Dr. Fee?
Yes, Prof.
2 on the dot. I think we can start now. Thank you.
Okay. Good afternoon, everyone, and welcome to the virtual discussion on the book titled Power Systems 4.0, Current Trends and Future Outlook. I am Dr. Vuyiswa Lotsoko, and I will be moderating today's session. This virtual book discussion really explores the themes and insights that are presented in Power Systems 4.0, which is really a timely publication that examines the evolution of power systems from analog foundations to digital smart grids and beyond into the era of the fourth industrial revolution and society 5.0. This session will be divided into 3 key phases, which in total should take up about 90 minutes. We will start with a book overview and key insights by the authors, where they'll present motivation for the book, a thematic walkthrough, some of its chapters, and some of the key takeaways that they would like us as readers to get from the book. And then we'd move into the expert panel discussion, where we will discuss 5 thematic areas with the panel, exploring topics that are covered in the book, such as smart grids, society 5.0, renewable integration, industry 4.0, and future grid infrastructure as well. We'll then move on to our interactive Q&A and wrap up of the session. And in the session, really, we'll be able to provide a session where people are able to provide question and answers, and they can engage directly with the authors as well as the panelists. And we'll then round up with some final reflections and along with some contact information that can be taken for continued engagement in the conversation. So in terms of the logistics, I mentioned that the session should be 90 minutes. So would like to ensure that all participants mute their mics to minimize any background noise and disruptions, and to remain muted unless, of course, invited to speak during the Q&A session. You're also welcome to use the chat box to post questions and comments throughout the session, and these will also be discussed in the Q&A session. Please be reminded also that this is a live recorded session, which is being streamed as well on the UJ Library social media pages. So without wasting much time, I'd like to take a moment to introduce the authors of the book. I'd like to start by introducing Dr. Mutegi Mbai, who is a consulting electrical engineer with over 15 years of experience in power distribution and retail, having worked with Kenya Power and other utilities across Africa and Europe. He also holds a PhD in electrical and electronics engineering power systems from the University of Johannesburg, along with a BSc and MSc degrees in the same field. He is passionate for energy access, zero emissions, and power systems. He has published numerous peer-reviewed journal articles and presented at international conferences, as well as contributed to book chapters on power systems as well. He also serves as a lecturer at the Jomo Kenyatta University of Agriculture and Technology in Kenya. And then the second author is Prof. Namdi Nulu. Prof. Namdi is a leading academic in electrical and electronic engineering at the University of Johannesburg. He has a strong background in research, innovation, and education, and also holds a BSc and MSc degree in electrical and electronics engineering and a PhD in electrical engineering as well. His research focuses primarily on digital technologies, mathematical optimization, and machine learning to food, energy, and water systems. He has authored several books and has over 200 publications, earning accolades such as the 2021 NRF Research Excellence Award and the 2020 UJ Vice Chancellor's Award for Most Promising Young Researcher. He is a registered professional engineer and a senior member of the IEEE and a fellow of the SAIEE, and is also a member of the South African Young Academy of Science. He currently serves as the editor-in-chief of the Journal of Digital Food, Energy, and Water Systems, as well as an associate editor for the IET Renewable Power Generation and the African Journal of Science, Technology, and Innovation and Development. So I think I'll just stop there for now, and then I'll introduce our panel of experts as we move on to the second phase where we have the expert discussions. But I know our authors have prepared a presentation for us where they will briefly discuss and take us through the book. And then after that, we will just go through some of the key questions on the book itself. Thank you. We can see your presentation. You may proceed, Dr. Mutegi and Prof. Namdi. Thank you.
Thank you so much, Dr. Fuyi. Thank you so very much for agreeing to do this at such short notice. And then good afternoon, everyone, and welcome to our virtual book discussion. Also a very good afternoon to the panelists from Kenya, from Arizona, Dr. Tam in Arizona, Dr. Tam in Arizona, here in Johannesburg, and I think the other doctor in Kenya. Thank you very much. All right. I will be speaking very quickly on I'm delighted to also be here with my co-author to share our new book, Power Systems 4.0, Current Trends and Future Outlook. This book essentially represents slightly over 2 years of research and collaboration between academia and industry, and we're excited to discuss it with our growth in variable renewable energy. This isn't just some gradual change. We are seeing dramatic increases every year with renewable energy capacity more than quadrupling since 2010, right? And this creates an unprecedented challenge for power system operators worldwide. However, renewable energy growth is just one piece of the puzzle. And we also have three major forces converging simultaneously. The first is the exponential growth in variable renewable energy, like I mentioned, which is fundamentally transforming how we generate power. Traditional baseload generation is giving way to intermittent sources that require completely new approaches to grid management. And the second key driver is Industry 4.0 technologies, which is finally enabling the smart, robust, and agile grid optimization and control systems that power system operators have been angling for decades. There are now IoT sensors, artificial intelligence, and smart communication technologies that can make smart grids a reality rather than just a concept. And thirdly, the Society 5.0 vision, which is driving us towards human-centered future grids. This is not just about technology, it's also about creating power systems that serve human needs in a more integrated and sustainable way. These three forces together create what we can call the perfect storm that's driving the transformation of power systems 4.0. To understand where we are going, we need to appreciate how far we've come. This evolution timeline shows the remarkable journey of power systems over 150 years for most of this period, from 1870 to 1990. Power systems remained relatively static. There was, of course, the advent of generation and transmission, followed by synchronized and centralized AC grids, and then, of course, the rise of HVDC for long-distance communications. But notice what happens from 2000 onwards. The pace of change accelerates dramatically. We see concepts such as energy sector unbundling, the emergence of smart grids, and now we are entering the era of energy 4.0, we think it is 2.0. And then looking ahead to 2050, we envision wireless transmission technologies and Society 5.0 systems. This evolution is not just technical, it represents a fundamental shift in how we think about energy systems. We are moving away from a model based on economies of scale to one based on intelligence, flexibility, and human-centered design. Given this rapid evolution, you might ask, why this book and why now? Let me give you a few compelling reasons. Global electricity demand has surged 6% in 2021, representing the largest increase since 2010. This massive growth is happening at exactly the same time we are trying to decarbonize energy systems. Second, power systems, like I said, is accelerating like never before. You have 100 years of incremental change compressed essentially into a few decades, arguably into a single decade. Innovations that used to take decades to implement in time past is now happening in months. And these two drivers essentially have created a critical gap between academic theory and industry practice in power systems. Researchers are busy developing sophisticated algorithms, but practitioners need practical guidance on how they should implement it. Our book seeks to bridge this gap. And fourthly, the African context requires specific solutions for our sustainable energy transitions, right? Our African power systems face unique challenges that we sought to also address in this book. This book, therefore, provides this comprehensive framework for both researchers who need practical applications and practitioners who need implementable solutions. It's written for everyone who needs to understand both where power systems are and where they are heading to. So this is the basic structure of the book, 6 key chapters. And then we've organized it in a logical journey from fundamentals to future vision. And I would hand over to the corresponding author and the first author, Dr. Ere Mutegi, to continue the conversation. Dr. Area?
Yes, thank you, Prof. And once again, our appreciation to the UJ team for agreeing to host this discussion within such a short time. We appreciate also the host, all our panelists for showing up and being part of this discussion. So we will continue with just a brief look at the book. As Prof has said, the book is organized into 6 key chapters. We are looking at where we are coming from as an industry. The journey has been quite long. That is largely the first chapter, followed by how the power system, T&D, transmission and distribution systems have evolved over time. As Prof lately noted, the evolution has taken perhaps 200 years from early 1750 to where we are, but the last decade has seen
Dr.
exponential.
Sorry to interrupt you. Can you just make it full screen?
Make it okay. Okay.
Your presentation. Thank you so much.
Thank you. Thank you. That should be okay.
Yes.
That should be. Thank you.
Yeah.
Thank you. So as I was saying, that's also Prof put it. We have seen the evolution of our system from more than 200 years, from around 1750 when a lot of the discovery started. But the last 10, 15 years have seen exponential growth, largely powered by the advent of fourth industrial revolution and now the society 5.0 we are talking about. And as a Prof also mentioned at the beginning, we have seen an exponential growth in the variable renewable energy, largely solar and wind. Again, as much as it's an opportunity, it also presents challenges in the power system, issues of stability that require to be handled. This is, of course, combined with the issues of industrial revolution that we'll be able to see. So the first chapter is basically an introductory chapter that we look at the long journey the power system industry, both practice, research, academia, has traveled from early in the century. We start off, of course, by looking at the various forms of energy generation. We are talking of basically mechanical to electrical energy conversion systems, hydro, wind, waves, etc. The chemical reaction systems, batteries come into play, solid state, and so forth and so on. And then we also just making a peek, or rather a sneak preview into the long journey that you're talking about in terms of the power systems. And the reason why we are looking at this is because also, as we see later, yes, the journey has been very long, but there are a lot of lessons in the past that keep on showing up here, and most likely they will also show up in future, both as lessons and challenges. As we said, the decade, or rather the century from 1750 around there to around 1850, so a lot of major discoveries that started off the entire industry. Around 1890s, we had the first AC transmission system line that was done in Germany. We had also around 1896 the first transmission of power from Niagara to Buffalo, that is in America, using an 11 kV line. As we say, even to date, many countries still use this as a distribution standard. And of course, that is just a few areas we are looking at. And the reason why we are mentioning some of those things is because you will see nothing much has really changed. Like I'm saying, 11 kV is still a distribution voltage for AC even today. That is more than 20 years later. So there are lessons we can learn from the past as we look at the future. In the same chapter, we are looking at the fundamental concepts of power systems circuits network analysis, where we are looking at issues, the basics of analysis in terms of power systems. We are looking at the network, what we call the mesh, that you use to analyze power systems, things like Kirchhoff's laws, things like Thevenin laws, among others. We also look at the basics of measurement. We have the 7 basic primary units and the other derived units. Issues of impedance is part of the derived units that is basically in the introductory chapter. So the chapter is quite rich, especially as I said, on the journey all the way from where the industry has started to where we are now. And one of the lessons from this chapter is what we call the conventional grid has become old and outdated. Today, for example, we require two-way flow of power, which the conventional grid cannot support. Today, we are looking at advances in technology for better integration of the variable renewable, better customer experience. Customers are now able to be both consumers and generators and so forth and so on. So as we look at the history, we are also looking at where we are within this chapter. We're also looking at what informs the future. We are talking of the virtual, for example, generation and transmission lines, which we'll see in subsequent chapters. The next chapter is largely on the power grid in terms of the transmission and perhaps even distribution network will fall into this chapter. And as we said, we are trying to marry, or rather to look at where we're coming from, lessons from the past, lessons at the present, and also where are we going in terms of the future, to enable both practitioners as well as researchers. In terms of the modeling of transmission lines, conventional lines, we normally classify them into 3, short lines, medium length lines, and lines. We are talking of the short lines being less than 80 kilometers to around, and carrying a voltage of up to 66 kV. Medium voltage lines around 80 to perhaps 250 kilometers, and carrying between 66 to 100 kV. And long lines beyond that. We have the pi models for the modeling and analysis of these lines. This is also what is modeled in a lot of the software we use for the analysis of power systems. This is now what is giving way into the future. This is what we have been doing for the longest. This is what we call the conventional grids. We have delved into a bit of the modeling, the existing software, the likes of Power Factory, DigIsland, MATLAB. I've all these my models that we have been studying for a number of years, and also that is what is used in many utilities and in many places across the world. But also what we are saying is this is slowly but surely giving way to what we call the virtual power plants and the virtual transmission lines. For the virtual power plants, we've looked at the model, how it is alive back in the book. We are talking of aggregation of generation, for example, within an estate to treat it as a virtual power plant. What we mean is, for example, if it is Johannesburg, you can have 1,000 homesteads generating, say, 10 megawatts within a certain estate. And these ones sign up to the local utility to deliver power. So the local utility, through the advanced ICT systems, is able to see those homesteads as equivalent to a 5 megawatt plant or something for purposes of operating that grid. Same thing with the modeling of the virtual transmission lines. The virtual transmission lines largely have come up to occupy one of the big challenges of power networks, which is basically congestion in the transmission grid. We are looking at a model that can assist in deferral of expansion of the network and yet uh, serve the need of taking care of a lot of the renewable energy that is being generated to the customers and so forth and so on. For the virtual transmission lines, on the supply side, we have the storage. And the storage in this case is modeled in a way that it stores excess renewable energy that can't be used when there is great congestion. Then whenever the congestion goes down, that excess energy is pushed through the grid, transmission grid. And of course, on the lower side, that is on the distribution side, we also have a storage, which discharges when the grid congestion goes down. So again, we have looked at the modeling of the two, which is taking over from the conventional lines that we have been modeling over the years. That is the short length lines, which is basically what we call the conventional grids. And of course, as Prof mentioned at the beginning, looking at the future, there is still room for wireless power transmission that will be perhaps what we can call no grid, no battery system, just about wireless system. And this is something that began in 1891 with research that Tesla used to do. There was what we call Tesla coil. And we look at it, it looks like many years later, when we're done with the conventional grid, the virtual power plants, we might still have to go there. Currently, of course, there are many challenges with this, which we have also modeled. We'll be able to see it later. When you talk about wireless power, of course, we are talking of at the sending end, we have the conversion of the electric power into microwave and laser beams, which are transmitted wirelessly to the receiver or the antenna side. And on that side is converted back to the power that you need. The drawback with this system as it is right now is there's a lot of the infrastructure is still very expensive and also quite inefficient. However, we are talking about also the advances in the fourth industrial revolution, post-fourth industrial revolution. So you're looking at a situation whereby metamaterials become even better so that this ultimately takes over. We are looking at situations whereby we might also have frequencies where we can transmit both power and data to make it even better. So this might be the ultimate frontier of the future. And so, if you look at this chapter, that's the reason why we have brought it out here, because we are coming from the conventional grid to the virtual plants which are taking over currently, not yet there in many places. Then the post-grid area might be the wireless. And of course, currently we have a lot of the smart grid, which is also part of what is covered here. So the modeling is well covered in this chapter, which gives way to the other chapter, which is basically on power system control and optimization. The reason why we're looking at optimization control in this case is because when we look at the exponential growth of intermittent renewable energy generation, the impact on grid stability is major. So there's need to see ways of taking care of that. We talk of optimization also because expansion of the grid is still a nightmare. Costs are high, land might not be available, well used to do those lines and so forth and so on. So the question of optimizing the existing grid, like we just saw, one of the ways of optimizing is using the virtual power plants and virtual transmission lines. We are looking at basically the ecosystem of optimization with in mind that the investment, the environmental concerns and all that are slowly becoming a challenge. Of course, the grid is becoming more complex. Controlling it is also a problem, rather a challenge. So this chapter tries to delve into all that, the basics of stability and control, the existing power system optimization techniques. We have the classical optimization techniques, that is basically the mathematical models. We have the sensitivity optimization techniques, whereby you play around with the input and output variables. For example, the Jacobian and all that. Of course, the challenge with the classical and the sensitivity tools is they have huge convergent challenges. They have difficulties in handling nonlinear systems, and also multivariable systems. Again, they have challenges in handling that. Where we are right now is the growth of meta-heuristic optimization algorithms. These are algorithms that have been formulated based on the biological systems, which of course they are more versatile, more agile, with better convergence capability when compared to classical optimization tools and the sensitivity tools. We are talking of the evolutionary meta-heuristic techniques, physics-based techniques, swarm-based techniques, and so forth and so on. For this particular chapter, we delved into one of the meta-heuristic techniques that we developed recently, that is the filter feeding allogenic engineering algorithm, just to showcase what we're talking about. So the authors of the book developed this one from scratch, just as a way of showcasing that what you're talking about, the possibilities are there, and what can be done so that we have better tools. So basically, the filter feeding optimization allogenic engineering algorithm is inspired by what we call the filter feeders. Filter feeders are what we can call ecosystem engineers that thrive by squeezing oceanic matter or other particles through their filtration system. We have autogenic engineers and we also have allogenic engineers. For this one, our inspiration came from the allogenic engineers, which work by moving materials in water by way of filter feeding. And of course, this movement is largely inspired by the concentration of the nutrients in the water. And of course, basically what we are saying is they act mostly as a ocean environment monitors. That is the inspiration that we have used to develop here, so that we use the same concept in a power system, whereby we are able to monitor. In our case here, we tested the active power and the voltage deviation profiles by modifying the predator-prey equations of the allogenic engineers, which of course we did the testing and got very good results using an existing grid. Of course, we benchmarked it using the well optimization algorithm, and we got very good results. The future of this, as we said, we are looking at the impact of AI and big data analysis in the development of more robust meta-heuristic techniques. The questions we're asking here is how better can we get if we utilize the ever-growing AI tools, the ever-growing big data tools. The next one is chapter 4. We looked at the opportunities, challenges for the increase in renewable energy. That is the intermittent energy. And as Prof mentioned at the beginning, especially solar and wind, the share is huge. Of course, it's a good opportunity, but in terms of the grid stability, presents its own challenges, which we have details in this particular chapter. Distributed generation is also taking over, especially because of the variable renewable energy. And this is exactly what Thomas Edison was pushing for all those years. So you can see the concept is still back many years later. We are looking at the opening up of the sector, the opportunities available within the entire grid in terms of the liberalization, generation, transmission, and distribution. And in this particular chapter, we have looked at 4 models that play a crucial role in the grid stability improvement as we increase the share of these intermittent energy sources. The 4 crucial techniques, one of them is the enabling technologies. We're looking at the storage, supercapacitors, flywheels. The second one is better business models. We are looking at what we call the energy internet, blockchain technologies, so forth and so on. We are looking at innovative market design, and also we are looking at innovative system operation. So within the chapter, we have gone into more details to explain how each of the 4 plays a crucial role in better improvement of the grid stability as we increase the share of variable renewable energy share within the grid. So it's an interesting chapter in the sense that we have very good models within those 4 categories that show perhaps what researchers can take up, what utilities can be able to take up and customize within their jurisdiction. As Prof mentioned, issues in Africa may not necessarily be the same issues as Europe and so forth and so on, but the models will not deviate too far from those 4 categories that we have talked about in the book. We have also done very good illustrations of all these models. Actually, the entire book has 49 illustrations, and all these 49 illustrations are what we have developed ourselves in the course of coming up with the writing. It's not models we picked anywhere. A lot of the illustrations we have developed in-house to better illustrate these points and to make them as simple as possible to the users. The second last chapter that we looked at is on the Industry 4.0, post-Industry 4.0, that is the 4th Industrial Revolution, and the impact of this on power systems. If you look at the Industrial Revolution, we started off with the first Industrial Revolution, which was largely agrarian, developed by, or rather powered by steam and water. We went to the second Industrial Revolution, which was powered by electricity, largely for mass production, which gave way to the third Industrial Revolution, that is digital technologies. Then we are now into the 4th Industrial Revolution. We are looking at a situation whereby, because of the advances in ICT, or other better improvements on the 3rd Industrial Revolution, we are seeing a situation whereby the differences between the digital, physical, and biological space is becoming very little, what we call the confluence. The meeting of the 3 spheres is giving very good opportunities, not just for power systems, but for any other industry. Digital technologies like AI, machine learning, big data, IoT, the physical technologies like robots, autonomous cars, etc. The biological space like biomedical engineering, genome editing, neurotechnology. All those spaces seem to be coalescing together and giving very good possibilities. And of course, for us here, we are more interested in the impact on the general power system space, which is also something that we have explored quite deeply within the chapter. And of course, post-industry 4.0, we are looking at society 5.0, which is a humanity-centered society in the sense that it looks at the general well-being of the people, happiness, better productivity, and the balance between social and economic integration as human advances continue. This is a term that was coined in Japan in the year 2016, but slowly but surely is taking over the entire space. We're looking at smart cities, smart grid, smart materials. The reduction of the space between man and machine is also real. The better utilization of data by looking at data, converting into knowledge for better decision making. So we have looked at a lot of the opportunities available for the power system space, right from generation, transmission, and distribution, the space for robots, drones, sensors, the space for big data, the space for smart grid, machine learning, and other digital technologies, things like digital twins, Internet of Energy, or what we call the energy democracy, blockchain, and so forth and so on. So the opportunities are endless. This is one of the things that we have extensively covered in this chapter, so that it can also help the decision makers, the researchers, and practitioners to take advantage of this emerging space, of course, for better decision making. So this is an interesting chapter also for anyone who is interested in power systems, as we try to make the future even more better, systems more efficient, the users also more happy, and generally better experience for everyone. So the final chapter, we have taken a bit more time to look at the post-industry 5.0, 4.0 and the power systems. That is the advent of society 5.0, what you have talked about here. The humanity-centered society, where you are looking at the happiness, proper use of the existing data, converting into knowledge, smart cities. So in this chapter, we have looked further at the opportunities for the power systems, the impact this is going to have on business models. For example, are we looking at situations whereby the Internet of Energy, for example, gives way to equivalent of energy stock exchange? Blockchain is a good example, which is already on that direction, what we call digital energy. How this is going to be coupled to the virtual generation, virtual transmission lines, the place for storage, the place for consumers who are also generators, how regulators can also look at this. Power system is basically a very highly controlled environment in terms of a lot of regulation because of a lot of government control. So again, regulation also needs to be a bit more innovative to move faster. It's also something that we have delved into. And if you look at history, someone like George Westinghouse and Thomas Edison, initially they were both in the power distribution space, but the reason why they left and they went to industry is because of the very tough regulation, because of government interest. Of course, Westinghouse started the famous ABB, And Thomas Edison started the famous General Electric, and the rest is history. But you look at the thing, many years later, we're still grappling with the same challenges. How do we loosen regulation for the many players who want to get into this space without compromising perhaps issues of quality and other issues? Of course, and having in mind that also energy is both a political issue and economic commodity. So this is a final chapter that we have looked at. Here we have two of the illustrations that are found in the book. As I said, we have 49 illustrations in this book, and all of them is what we have developed within the time we have been working on this project. So once again, thank you very much, and thank you for giving us time to just give a sneak preview into the book without going into a lot of details. Thank you.
Thank you, Dr. Motegi and Prof. Namdi, for that detailed overview. I think it's evident that a great deal of effort, expertise, and thought went into the development of this book, and the depth of the analysis and the clarity with which the complex concepts are presented also make it quite a valuable contribution to the field of power systems, especially, of course, in the context of a rapidly evolving global energy landscape as well. So I had two questions, but I think in the interest of time, I think I'll just, ask one, and then that would maybe just lead us into the next session, which is the panel discussion. Writing a book of this nature, of course, often uncovers new insights and challenges, as well as assumptions about power systems. As you conducted your research and engaged deeply with the evolving landscape of power systems, were there any certain patterns or discoveries that may have stood out? And specifically, what were some of the most unexpected or surprising findings that emerged from your research?
Thank you. What we can say is, if you look at the space, especially within Africa, we are still very slow in uptake of the great opportunities that are available in this space. And the opportunities is both for the governments, that is the utilities, the customers who can be both customers and generators, and also the general public. Because what we have seen is we don't really have to copy paste a lot of these things. We can customize a lot for the local situations. For example, the situation in Johannesburg is not necessarily the situation in Nigeria or Cameroon or even Kenya. So in the African space, we are still not yet very adept in moving in this direction. And is one of the inspirations of that side to come up with this work. Thank you.
Okay. All right. No, thank you. Thank you for that. I think, that leads us to the next part of the session, which is the panel discussion with our experts. We've got three experts here with us. I'll just briefly just go over their profiles, who are just going to, carry on with the discussion in terms of some of the key concepts and the reflections on the book as well. So we've got with us Prof. Johnny Dladla, who is a former interim group CEO of Eskom and CEO of Eskom Enterprises and Rotec Engineering. He currently serves as a professor of practice at the University of Johannesburg Center for Cyber-Physical, Food, Energy and Water, where he acts as a bridge between industry and academia by bringing valuable insights from utility management into the academic sphere. He has over 30 years of experience spanning engineering services, transformation, and empowerment strategies across public, private, and civil society sectors. He's known for aligning strategic intent with technical execution, as well as fostering innovation and advancing the engineering ecosystem. He is also a respected leadership coach and a mentor to CEOs and professionals across the energy, engineering, and technology sectors as well. We then also have with us Dr. Tam, who is a distinguished energy expert and researcher who in driving innovation in sustainable engineering access as well as solutions for global energy poverty. As a co-founder of Intric Power Systems, he leverages his expertise to develop impactful projects. Dr. Tam's research focuses on energy transitions, power sector transformation, and electrical power systems, with influential papers published in leading energy journals as well. His work aims to drive positive change, particularly in West Africa. And Dr. Tam holds a PhD in sustainable energy from Arizona State University, and he also works as a postdoctoral researcher in the same university. We also have with us Dr. Roy Orenge, who is a seasoned electrical engineer and energy systems expert with a strong background in renewable energy, power system modeling, and energy regulation. He served as the head of Department of Electrical and Electronic Engineering at JKUAT from 2020 to 2024. He holds a PhD in electrical engineering with a research focus on solar PV integration. He also holds MSc and BSc degrees in electrical engineering as well, and with professional certification in energy regulation from Florence School of Regulation in the US. His work spans academia, consultancy, and research, where he contributes to projects on energy policy, electric mobility, and renewable energy feasibility. He is a registered professional engineer, a corporate member of the Institution of Engineers of Kenya, and licensed by the EPRA for electrical and solar PV installations. He actively contributes to the energy sector, peer review and participation in professional committees, and has published widely and presented internationally on topics related to power systems and clean energy transitions. So welcome, gentlemen, and I'd like to bring you into the conversation. And perhaps we can start by reflecting on the evolution of power systems, which, as Dr. Muteri was taking us through the book, we see that the book traces the journey from conventional to smart grids, also looking at power systems evolution and smart grids specifically. So, Prof. Latha, maybe I can bring you in here. Based on your experience at Eskom, how realistic do you believe this transition is?
Thank you, Dr. Vue, and thank you to the authors for inviting us to be part of their journey to this exciting, book that they've put together. It just brings a lot of nostalgic reflections, just reading the book itself. Having worked in the industry for over 30 years, these were the most challenging periods. And I can tell that the book Smart Grids Vision is compelling. However, it faces significant practical hurdles. For instance, there has been some basic infrastructure maintenance challenges while trying to implement the digital solutions. The reality is that in most African utilities, they are still dealing with aging equipment from the 1970s and 80s. I think we are experiencing that in the country as well. The positive, I guess, signs is that there is focus in terms of how this can be resolved. There's a lot of attention and infrastructure, programs and support from government, and the private sector has also joined in in making sure that it happens. However, until that is concluded, it remains a challenge that needs to be focused on. Again, if you look at, to your question on how realistic is this transition from conventional smart grid, as described in the book, is that if you look at the DSM, demand side management problems, South Africa started looking at what could work from an energy security point of view, it did show that if you give customers real-time information and you incentivize them, they respond remarkably well. So those are some of the wins that we can leverage, based on what has been done in the past and seems to have worked. Again, the technology exists, but there's requirements for investments that, coupled with addressing the skills gaps, that is quite enormous. And the two, scholars have looked at, how that can be addressed. I think when you look at the chapters in the books, they are somehow addressing those the suggestions and proposals as to how those gaps can be bridged. So I'd really say that a phased approach, starting with smart metering and moving into basic automation before attempting the full grid digitization. So that's my takeaway from the book, based on the experience that I've had in the industry. Thank you.
Thank you, Prof, for that. I mean, the transition to smart grids is often presented as a critical step in modernizing power systems and specifically in improving efficiency. However, of course, implementing such systems, particularly in resource-constrained settings that you've just touched on, Prof. Dlada, comes with significant technical hurdles as well. So, Dr. Arenge, perhaps I can bring you in here to just provide your reflections, and based on your experience with grid integration modeling and renewable energy systems, what would you say are the key technical barriers to smart grid implementation?
Thank you so much, and I think I'll join the other professor in congratulating the team that authored this book. I think this is one of the most all-rounded book that I've seen, that you're looking all the way from the advent of power systems, and now you're even having something on how the power system is going to be in the future. So thank you so much. I think this book is it's quite eye-opening, and I can't wait for it to be published and share it with my students. And that is it. So into the question, I think smart grid, as likely as it was put by the presenter, Engineer Mtegi, it's something that really is the future of the power system. And when we look at it from the African perspective, and even how other industries have been able to integrate their grid, or rather smartening the grid, the challenges that are always there are mainly looking at advancing, basically, how do we modernize the grid? How do we modernize the grid? How do we ensure that we have stable communications and all that? And sometimes the challenges that are there more or less to do with the existing system, like the power systems that we have right now. Someone mentioned during presentation that we have a lot of infrastructural issues. The grids as they are quite, if we lack a better word, we can say they're quite outdated. And in that particular case, then to have a well-established smart grid, we need to modernize our grid. And that can only happen if we have a lot of budget allocations towards grid modernization, which competes with the basic challenge of lack of 100% maybe grid connectivity in most places in Africa. I think even from where I come from, we are still not able to get everyone electrified. So now the question comes, is it, do we get them connected with an old grid, or do we start modernizing the grid that we already have? So those kind of challenges also make us, or rather makes smart grid, or rather introduction of smart grid a challenge. So we have the technical, we have financial, and even sometimes lack of capacity in terms of the human resource to be able to transition the existing grid to the smart grid. So I think that is what I can say, that looking at it is in summary, is a technical problem, is a financial problem, and also it is a policy and a priority issue that is facing most of the African states. Thank you. That's all I can say for now.
Yeah, thank you. Thank you, Dr. Renge, for that. And perhaps Dr. Tam, drawing from your experience in sustainable energy transitions and work specifically in West Africa, maybe you can just share your views on how this shift perhaps impacts energy access in developing economies, just to add to what Dr. Renge has already touched on.
Thank you for that question, and also thank you to the host for the opportunity to be here today. I really appreciate the chance to have been able to review the book even before it was made public, and also to present some of my thoughts and some of the questions being asked. So maybe we could step back a little bit and think about the idea of a smart grid, because we use it a lot in the industry and it's not as common as we think it is. For example, even across the world, even in developed or developing countries, the idea that most a utility would understand where its asset is, able to communicate across its system, especially on the distribution grid. But for what I would say is, when we come to the context of Africa, is looking at, because of the current state of our traditional grids, where infrastructure is pretty old. A lot of the infrastructure we have were built either pre-1960 or around that time. And to even think about upgrading those systems, we need fairly financially viable utilities, and that is not yet the case. But what we're seeing in some of the work we've been doing across electrification on the continent is that developers who are building mini grids, communities that are usually off-grid, are actually developing those systems based on the tenets of a smart grid, which the idea of being able to use smart metering, so you can easily understand who is, on the system or off the system. You can understand who is stealing electricity from the system. You can shut people off remotely. And we're seeing this across some of the different projects that are being built in Nigeria, in Kenya, in Sierra Leone. And I think the issue here is now, how do you integrate this to the larger grid, right? And that is where the problem becomes a little bit more complicated, because it's not a technical problem per se. I would argue, actually, that we do have the skill set to design smart and operate smart grids, because we are currently doing it. Many developers who develop mini grid projects in remote communities are doing it. So, for example, I could log into some of the systems that I've developed from anywhere I am in the world. I can understand how the system is operating. I could turn meters off. I could turn meters on. And in some cases, our systems are designed to actually be self-healing. So if a breaker opens because there is a quick of faults that happens, maybe due to an animal that runs across the system, it closes back. And if that fault is still there, then it opens. Then, crew has to go out and fix it. But to expand this across the entire continent, especially the sub-Saharan part of the continent, would require, I think, addressing some of the regulatory issues that we've been seeing affecting the way some of these utilities are financed. Many African utilities do not charge customers cost-reflective tariffs. That affects their ability to have enough capital to reinvest in their infrastructure, and they're not able to upgrade many of their assets to the point where an operator could have almost near perfect situational awareness of all its assets, of all its customers, is able to reduce electricity theft, and able to manage and operate the system safely, and also increase the quality of service. Because if you have good situational awareness of your assets, and for example, a part of the grid or the distribution system has an outage, you know automatically that there's an outage, and you can send a crew out there. You don't have to wait for people to call you to tell you that there's an outage somewhere. Then you have to send a crew out there. So you're able to improve your quality of service. And I think figuring out this regulatory aspect of how major utilities finance themselves, which boils down to the cost-reflective tariff, being able to make enough revenue to address, to reinvest into an infrastructure would be, I think, a major issue of addressing the smart grid evolution when we think about energy access in sub-Saharan Africa or in the global south at large.
Thank you. Thank you so much for those views. I think you've also made us think about something interesting as well with regards to the regulatory frameworks and the opportunities and the challenges that are there as well. So now I just want to move to another concept that is outlined in the book, which is Society 5.0 and future power systems. The book outlines that the future of power systems is not really just about technology, but it is also about placing people at the center of energy planning and decision making. And the concept of 5.0 reflects a shift towards systems that are more inclusive, responsive, and tailored to human societal needs. So with that being said, Dr. Tam, can I just bring you back into the conversation to ask really, what does a human-centered power system mean, specifically for sustainable energy transitions, particularly in the developing context, considering what you've just mentioned now in terms of some of the challenges of the global south? Thank you.
Yeah, I think that because the idea of energy regulation is that we, as much as possible, want to build large infrastructure where we pay for it by spreading the cost across multiple people. So everybody kind of pays their fair share for having this large infrastructure, because electricity benefits from the economies of scale. So the larger you are, the larger your system is, the cheaper electricity is. And because of that, we operate a model of quasi-judicial processes to regulate electric power sector. So essentially, everybody is supposed to be able to participate in the way we operate the system, in the way we come up with quality of service rules, in how much tariff we charge customers. And because of that, you have these regulatory agencies that are very, very common across different jurisdictions, or in some cases you have some type of utility board where people are able to lay complaints about how the utility is providing them electricity and some of the problems they have. So in that regard, I think that our power systems are fairly people-centric, But the issue is, how do you operationalize that? We see many cases where regulators are not necessarily independent enough from the broader political vicissitudes of the country, and are not able to make proper decisions for the power system. Then operationalizing that in the context of sub-Saharan Africa, I think many people are not necessarily involved as they should be in the decision-making process of their utility, just largely because the quality of service is poor. They don't think that if they make complaints, they will be listened to. But again, going back to some of the communities that are usually, will be termed off-grid or remote communities, where we see developers building projects in those communities, we are seeing a lot of community participation in those systems. So a developer goes into a community, usually would set up a meeting with some of the elders of the community. Then everybody in the community will show up one day for a meeting, and they would, explain what they plan to do in this community, the system they plan to build, the solar panels, the battery system, and in some cases, the diesel gen sets and the distribution system they're going to build. And the community agrees to a tariff, and they go ahead and build it. I think that's the definition largely of a people-centric system. So in the case of sub-Saharan Africa now, maybe the answer is the more decentralized systems, the more we get people much more interested in how the electricity is provided to them. And maybe we can scale that to the larger system. So instead of going top down, which is much more common in the industry, we can go bottom up, because that way we get to understand, or your utility gets to understand what customers need, because at the end of the day, electricity is what electricity can do in your life that makes it valuable. You can read a book, you can do your dishes, you can cook your food at the same time with electricity. If you didn't have that, you wouldn't be able to do all that. You have to do that one after the other, right? So people would then have much more, or the utilities or developers or electric service providers would have a closer relationship with their customers, going from the decentralized structure maybe to the much more centralized structure. Because still, except technology improves, electricity is made cheaper and much more cost effective as you go larger. So the larger the system is, the more per kilowatt hour, the lower per kilowatt hour you generate electricity. So there's still value in building large systems, but maybe in sub-Saharan Africa, the strategy might be to go from the bottom up to create this much more people-centric energy system that we talk about and that the book mentions quite a bit.
Okay, thank you, Dr. Tam. I'd like to bring in Prof. Dladla. Dr. Tam touched on the decentralization of systems and stuff. So I just want to get your views in terms of how feasible is the Society 5.0 vision, specifically for African utilities, considering your experience.
No, thank you, Dr. Boyo. What's encouraging for me in terms of the approach, focusing on Society 5.0 and future power system, is that it's human-centered. This approach resonates deeply well with my experiences, having worked in the townships and the rural, doing rural electrification. If one looks at the goals of Society 5.0, they talk quite well to the impact it will have on the society, which will be quite immense. Because if you look at the three key goals, there could be more, but the ones that are picked up from the book is it touches on the economic growth, which will help in driving innovation and prosperity. It also touches on social well-being, which we're looking at improving and enhancing the quality of life. And then the one that I also picked up was the environmental sustainability, which really will be promoting the protecting the planet for future generation. So if you look at it from that point of view, is that the potential impact this will bring is the improved healthcare, smart cities that my fellow panelists have touched on, and also importantly, enhancing education. And this book, for me, it's just the beginning. I'll see more of the revised versions of this book as we continue to have these engagements. So I would say really, if you look at the technology, we've learned that technology adoption depends heavily on the community. If there's no buy-in and understanding of the local needs, it becomes just an academic exercise. So the book, I believe that it just aligns quite close with the research work that we do at UJ when we look at the food, energy, water system nexus, because the research that is picking up as we continue to seek deeper and to contribute to the body of knowledge is that Society 5.0 requires an integrated thinking, which is exactly what Africa needs. We can't solve energy problems in isolation, and the book does highlight, the need for us to continuously search for possible solutions. Lastly, which may sound a bit negative, but is that the book timeline might just be optimistic, too optimistic. African utilities are still transitioning from basic service delivery to customer centricity. However, what's positive about it, though, is the vision. The vision is right. We need to build foundational capabilities first. And also the good news is that community engagements and stakeholders in the industry, especially, we require the continuous engagement frameworks. Having moved from electrification programs, using that as a blueprint for this human-centered approach, the book should also consider where to from here. And I think the grid infrastructure now is where the focus should be, because with all the investments that have been, targeted at improving the infrastructure and grid, as we increase the energy availability and capacity, if there's no way of executing that power, it will start, talking exactly what I was referring to in terms of being too optimistic as to where we're going. So we need to make sure that there's an integration of all these interventions, both from the industry, the academics, the businesses, making sure that we understand fully what Society 5.0 is encouraging, because if the community is not in the center of all what is happening, again, you just find a lot of white elephants structures because you're not addressing the problem. For you to come with the solution, there must be a problem that you're addressing. I'll pause here. Thank you.
Thank you. Thank you so much, Prof, for those insights. I just want to then move on to the concept of variable renewable energy integration that Chapter 4 of the book focuses on quite heavily on renewable energy challenges, integration challenges. Dr. Renge, perhaps you could just briefly, based on your solar PV research, outline for us what are the most critical challenges that are addressed with regards to this in the book. Dr. Renge? Okay, so I think maybe Dr. Renge is maybe struggling there with a bit of network. Maybe we can just move on then to the next question, which is something that Dr. Tam also briefly touched on, which was the aspect of energy democracy and the Industry 4.0 impact as well. The book discusses Industry 4.0's impact on the concept of energy democracy as well. And Prof. Dladla, I guess based on your experience, or how does your experience really connect to this whole concept or idea of energy democracy?
Thanks, Dr. Bui. I did highlight earlier, actually, when I touched on the demand side management programs, that, it was like an energy democracy in action. So the examples here, which I briefly touched on, was when customers are given an opportunity of being in charge. That is encouraged by providing information to them and incentivizing them. And we found that those programs worked quite well because when ESCOM, took the initiative of being proactive about, yes, we see that there's challenges now with more customers connecting to the grid, which was a nice problem to have in the country, in a sense that, we're redressing and addressing the past of communities that have never enjoyed having electricity. Now, when all of them were now connected, it was like, oops, we need more now. What do we do? And you start looking like a bit of a schizophrenic when you tell people, I give you electricity, but then you start telling them not to use electricity. Now, as a country, we had to look at how do we make sure that we balance this. It was a nice problem to have because it did call for thinking outside the box, and one of such was management programs. Government took up quite positively on it. They practically supported the programs. And what also that did was it also helped in educating the country that in as much as, would like everybody to have electricity 24/7, if there isn't enough of it, the risk of allowing the grid to collapse was more dire than being able to manage it. They use it, but use it reasonably so. So that program helped because government actively formed part of this program. We all became partners in grid management rather than just consumers. This taught us that when customers have information and incentives, they make rational decisions that benefit the entire system. When I look at the book, I think the book's vision on prosumers instead of consumers and distributed control, it builds on these principles. So I think to the authors, that for me, I think is one of those nuggets that, if anything else, one can build on in applying the knowledge that you are picking from the book. However, I think it's also important to highlight that energy democracy, it requires regulatory frameworks. I think the program director, Dr. Bui, you touched on the regulatory, in terms when you made your opening remarks. We need the regulatory framework. Say this, it's work in progress. It is receiving focused engagements. However, the energy regulators, I think they need to pick up speed in making sure that those regulations are quite clear and unambiguous. And we also require participation of key industry stakeholders, and I'm talking now policymakers, the regulators, stakeholders, the practitioners. I think you touched on as well on, when these regulations are in place, how do they help the practitioners or implementers, to leverage and see them as enablers of carrying on their business and doing what is required. Lastly, I would say that we also need reviews of policies. I believe that will allow peer-to-peer and and if you look at also the technology has to be ready, but the institutional frameworks require more attention, to enable that to be implemented. Those are the few points that I can share for now. Thank you very much for the question.
All right, thank you, Prof, for that. I think there's so much that this book covers. I don't think we'll do justice to every aspect or concept that it touches on, but I think maybe as we move towards a close, one of the key areas that the book discusses is the vision for future grid infrastructure. And we know as power systems evolve, the concept of wireless electricity transmission, which was once thought as being futuristic, is now gaining traction, particularly if we consider in the context of reducing infrastructure costs as well as reaching remote areas. So, Dr. Tam, do you think wireless technologies could help leapfrog traditional grid extensions in contexts such as your rural and off-grid communities in developing countries that still lack reliable access to electricity?
I think that if the technology definitely gets better and when we convert electricity to microwaves and move it, we don't lose a lot of energy on the way. I definitely think that would be a solution. I do think that technology is still a long way from being viable. Because, I remember 10 years ago when the idea was that solar and battery would help Africa leapfrog the entire world, and, we would be able to have universal electricity. That is still not yet the case, and solar and battery and renewable energy technologies are being used in the developed world also as much and even more than in sub-Saharan Africa. So I would be cautious at the idea of leapfrogging, because I think that it also removes the responsibility from regulators, policymakers to figure out the system they have right now. Fortunately, by some twist of nature and technological development, we're able to use mobile communication that was able to leapfrog the entire continent and basically transform how we communicate today in Africa. And maybe that's going to be the case with power. But and if we can safely do it, that would definitely be the case. But again, remember, we were not waiting to leapfrog when mobile communication was available. It was that the technology existed, it was pretty good, and we used it, and then we leapfrogged. So the idea of leapfrogging, I think, should be ex ante, ex post, and not ex ante, if that makes sense. So we have a responsibility right now to understand that our system needs to transform fundamentally across board. And maybe the simple solution is a cost-reflective tariff that can help with the financial situation of many of these utilities, because there is no single African utility that has investment grade credit rating, even Eskom. none. It used to be ESCOM, but now none of them do. And if we can figure out how to improve that in itself, I think that we can start addressing many of the problems we have. Leapfrogging should be something we talk about in retrospect, not something that we're planning for, if that makes sense.
No, thank you. Thank you for that, Dr. Tam. I think we've got 2 minutes left of this session. I don't know, maybe the audience, you could just use this opportunity to just type any other questions or comments that you may have in the chat. And while you do so, I maybe would just like to invite the authors once again to just share some final reflections. Specifically, what should readers focus on first when engaging with Power Systems 4.0? And are there any particular chapters or concepts that you would recommend starting with to gain the most immediate value of the book?
Dr. Ariel, do you want to start?
You can start, Prof.
No, I think from the reflections that we have when, let me say my own personal reflections when I contributed to the book, because it was Dr. Ariel that took the lead. Of course, it's stemming from his PhD work. What I would like to say is that most of the problems that we have from the power system perspective are not necessarily technical, right? In many respects, the technical aspects have been taken care of, right? Obviously, there's still room for research in terms of, say, improving the efficiency of solar PV panels, and all of that. They're still looking at various battery storage materials. There's still room for improvements, right, in the research domain. But by and large, the technologies are fairly robust. They are fairly reliable, right? So it's a case of African nations, in a sense, coming up with systems that work for them, from the regulatory perspective to cost-reflective tariffs to peer-to-peer trading. We have to come up with a case of not just essentially transplanting policies. And there was a time that vertical disintegration was the main thing, and most African utilities wanted to pursue that, right? And after a while, some countries that did pursue that and then deregulated their power systems. It did not also translate into more reliable power, right? So my viewpoint is that the socio-economic dynamics, right, are also as important, even more important in the African context than the technical dynamics. So just like did allude to, and Prof. David also did say, whilst we I think in my response is one of the questions I saw in the chat, where the student was asking about interest in postgraduate research, right? AI and power systems, in a sense that also leverages on the technical aspects. And I did say now that you must look at issues also around energy democracy, some of those socio-economic aspects, because that's where we can really unlock value as Africa. That's where we can come up with our own Afrocentric approach and then get the value or our people can now really and truly enjoy the value of real power supply, modern power supply, reliable power supply at the right quality, essentially energy security. So that's for me, Dr. Ariel. Thank you.
Thank you, Prof. I don't know, Madam, do you have a minute? I can see her hand is up, or we just she can deal with it later.
Yeah, I think maybe you can just provide your final remarks and then we'll take the hand. I think it's just only one hand, and then we can conclude. Yes.
Well, thank you, Madam, and thank you everyone for attending this book review and book launch. We are happy with the discussions. We look forward also to more engagements beyond this. The input from our panelists, we cannot take it for granted. Prof. and Dr. Orenge, we cannot take it for granted. So picking from where Professor Nulu has picked up, and also I think Dr. Tam came out strongly on it. The main challenge in Africa is developing our own solutions to fit within the context of our challenges, looking at where we want to go as a continent and also as individual economies. For example, the issue of integration of the grid across the continent to take care of, or rather to take advantage of cheap resources. Across here, we have Ethiopia that has abundant water, the DRC Congo, same thing, and across other economies. What we are looking at in this book is from the context of students, we were looking at inspiring students in terms of the research work. Professor Noor just answered one of the questions that was on the wall, I think, about a student who is interested in postgraduate work. That's one of the objectives we have here. We are looking at the industry. Prof is very strong in that, having been the CEO at ESCOM. The issues of grid stability, they are not just here. The other day we saw widespread outages in Portugal. And when we look at the whole thing, it revolves around grid stability. So it's not just an African problem, but also a global issue. And when we customize our own solutions, we are more likely to get it well. Issues of grid congestion, issues of capital constraints, I think all the panelists were very strong on that. The sustainability of what we have on this side is still a long way to go. That is a financial sustainability. We are looking also at research, AI, optimization algorithms, the intersection of these two, how we bring in the entire society, that is the general well-being of the society, the post-industry 4.0. So basically, power or energy in this case is the intersection of power is around the economy, is around social aspects, and it's also around the national politics. Divorcing power from the national politics is hard, and yet it is an economic enabler that you need to grow the economy, and also the social elements. When everyone is powered, the last mile of the customers who are out of reach of the conventional grid, the standalone grids we are discussing here is part of the social integration of everyone within the context of their economies. And so it is something that power is one of the few commodities that you cannot ignore government, neither can you ignore industry, researchers, and also the common person, who we are also saying can be both a producer and a consumer of energy. So those are some of the issues we are trying to tackle here and bring it out strongly. And we hope that in future we'll also have a better way. We hope also to inspire more of solutions from within the context of Africa, sharing experiences, because we know our problems are not very different across various countries. So once again, thank you very much.
Thank you so much for that. I think we can take Nthabiseng Ramoroka. You've been unmuted, so. Nthabiseng, are you still there with us? Okay. I think without wasting any time, I think there's maybe a bit of a challenge there with Nthabiseng's mic. But I'd like to close or bring this session to a close, and I think the conversations we've had today highlight the critical importance of bridging research and practice, especially in the evolving landscape of power systems. And while we're closing the formal discussion, I think the ideas shared here are far from final, and they open up a space for an ongoing dialogue and collaboration and innovation, particularly as we navigate the challenges as well as opportunities that we face in Africa's energy future. And I think the book has really provided us with that opportunity. So we encourage you to keep the conversation going beyond this platform, and really to engage with the book, share it with your networks, and reach out to the authors for continued discussion. For instance, in Ntabi Singh, we weren't able to hear your question or your comment that you had, but please do use the outside platforms outside this conversation to pose whatever question or comment you may have. Once again, thank you for joining us. Thank you to the authors for this discussion, and as well as the panelists for availing yourselves, as well as the participants for joining in this rich and thought-provoking session. And yeah, I think we can close the session. Thank you once again.